Hey everyone, it's Joe and welcome back to RAD103 Module 3, Lecture 4.3. And we're talking about QC of our imaging equipment. And we're starting off today by talking about exposure timer accuracy. The X-ray equipment that we use have timers for doing different things. And we've talked about a couple of them in this course so far. The first one that we talked about was when we're talking about milliamperage times time. We know that mass is whatever the milliamperage station times a certain millisecond amount of time. Sometimes we go into seconds, but for the most part, our exposure length, how long are we shooting X-ray for, is going to be a very quick, sudden burst of X-ray. So we have some exposures that are less than 10 milliseconds, so it's an extremely fast amount of time. 10 milliseconds is not long, and so the act of actually shutting off that timer takes time. And since we're dealing with such a short amount of time, the accuracy has to be within 20%. That's kind of a lot of leeway when you're dealing with something so quick. So 20% for any exposure less than 10 milliseconds, it must be within 20% accurate of the timer that's being used to calculate the timer accuracy. For exposure times that are greater than 10 milliseconds, you have to be a little bit more accurate because with that much time, you actually have time for the timer to shut off. So exposure times greater than 10 milliseconds must be accurate within 5%. And so once again, we're going to use a clock that's calculated or calibrated to measure within that amount of time. And so when those two stopwatches come together, those exposure times should be matching up pretty much together, or at least have no more of a difference than 5% for any exposure greater than 10 milliseconds. The other timer that we've touched upon is with automatic exposure control, AEC. And I've mentioned that if you have a person, let's say doing a chest or an abdomen, and they're quite large, and you did not adjust your technique for that large body habitus, there's a backup timer to make sure that the person doesn't get overexposed. So the backup timer should be an exposure of no longer than 6 seconds, which is eternity when dealing with X-ray, or 600 mass, whatever comes first, it'll automatically shut off that timer. And so we have to make sure that that timer is appropriately set. There's really no numbers to really remember with that type of timer. The ones you need to remember for the registry, the ones you need to remember with my test, is that if there's an exposure timer that is showing time of less than 10 seconds, it must be accurate within 20% of that time. For any exposure greater than 10 milliseconds, the exposure accuracy should be within 5%. All right, here's an old slide, law of reciprocity. I know we've gone over this several times, but we're about to talk about linearity. And I just want to remind you again that with different milliamperage stations, you can set appropriate times with that and still get the same amount of X-ray coming out of the tube. So I even have this bottom one, which is a little outrageous. You wouldn't have 2 milliamps. But anyway, 2 milliamps with an exposure time of 30 seconds will still give you 60 mass. It's still the same amount of X-ray as if you use 200 milliamps with 0.3 seconds. So let's talk about linearity. Let's talk about reproducibility. But just a quick refresher on the law of reciprocity. So exposure linearity is just making sure that this milliamperage station and this milliamperage station is indeed, they correlate with one another. So this really here, if you use the same amount of exposure time, should give you twice the amount of dose. Okay? And so this is just showing you as an example. This is the math behind it. You do not need to know how to do this math. You do not need to know how we got this. But it's just simply showing you an example of how linearity can be calculated and completed. This example of linearity shows that if you have 50 milliamps and you're going to go to 100 milliamps and you have the same amount of time, your overall intensity or beam intensity, it should just be double. And here for the example, you're going from 0.24 to 0.60. That's more than double. This should be around 0.48 if I was to double this intensity. So there's a problem here, and that's why we have a failed test for that, for going from 50 to 100. That is a failure. But my linearity from 100 to 200 was a pass. So you don't have to understand this math. You can follow it along if you want. You don't need to know it for the registry. You just need to know that if you set your milliamperage and you go up with the same amount of time, you go up a milliamperage station, the dose should be within 10% of each other. That's what that's what linearity is. So linearity looks at adjacent milliamperage stations, use the same amount of time, you look at the dose, and you should be able to calculate whether or not it's within 10% of the dose above it. So that's what linearity is. Reproducibility looks at just repeated exposures, the same KVP, the same mass, and you take exposure after exposure after exposure, and each time you're measuring the amount of X-ray coming out of the tube, every time you get a reading, they should all fall within 5% of each other. And so that's the way you do reproducibility. It's pretty simple. You need to remember the plus or minus 5%. And so those are all the tests that the medical physicists will do on periodic monitoring. But there's other QC that has to be done on the monitor itself, on the digital display. And so let's talk a little bit about that. When dealing with the digital display, we have to look at the pixels and the brightness of those pixels. We have to make sure that there's consistent lighting throughout the whole monitor. If one part of the monitor is a little dimmer than the other, that's going to obscure the image a little bit. And just making sure that, again, all of those pixels are showing the proper amount of brightness, and we're able to distinguish or see or visualize different changes in contrast throughout the monitor. So the first thing we're going to talk about is luminance response. And what that is we want to make sure that the amount of light coming through this monitor is uniform throughout. And we do that by using a photometer. A photometer can measure the amount of light coming out, so you can just touch it right onto the monitor itself, and it will measure the brightness of those pixels at that position on the monitor. And there's different things that we can do with that. But we want to make sure that we have that uniformity throughout the whole monitor. Otherwise, it's going to throw off your contrast, it's going to throw off your brightness levels, and you'd like to have it, measured throughout. Now, there are different kinds of photometers. You don't need to know about that. Just know that in order to measure the luminance coming out of a monitor, you use a photometer. You pretty much just stick it right on the monitor itself, and it measures the light. Pretty simple. This slide kind of gets into the weeds a little too much, I think. But what it's basically saying is that you want to make sure that whatever is showing on the computer or showing out of the monitor is indeed what the values were of the acquisition pixels of your plate. So it's the relationship between the displayed luminance and the input values of a standard display system. So we want to make sure that all of the digitized numbers, all of the digitized pixels from our acquisition plate are accurately being shown through the display. I wouldn't get too caught up with that, but we just want to make sure, once again, we've got a uniform type of brightness throughout the whole thing. The shades of gray that are being used are based upon the lookup table that you've selected for the exam. The grayscale of all of the shades of gray being used for your exam is based on, yes, all of the different bit depths of all of the pixels of your display. The other thing to be aware of is that whenever you're reading an X-ray, the best way to get the best contrast, the best detail out of any image is by looking at it straight on. Not from the side, not from the top or bottom. You want to be looking straight at that monitor, and that will give you the best visual display of whatever it is you're imaging. Now, in order to measure and calibrate displays or monitor displays, we had to come up with some tests in order to show that there is no degradation of pixels, to make sure that we're getting the spatial resolution that we want. We want to make sure that there's no type of geometric distortion. We want to make sure that the resolution is uniform throughout, and to see if there's any display noise that is causing any problems or any type of artifact on our image. And so a group called the task group, this is from the American Association of Physicists in Medicine, came up with these devices to be shown on displays in order to determine if there's any problems with geometric distortion, reflection, luminance, response, display resolution, and display noise. So let's take a look at those. Now this is the standardized QC pattern used for monitors. It's called TG18-QC. You should be aware of what this grid pattern is and what it's called. And so whenever we get a new monitor, or a doctor gets a new monitor, or whenever a manufacturer comes up with a monitor, they're going to judge its QC most likely based on this type of grid, which will show on the monitor to show if there's any distortion, to make sure all pixel values are there, the level of contrast that we require is being present. So you can take a look at it. Just understand that this is called TG18-QC, and this will likely be on your exam, and you should just be aware of that. All right, we're almost done, folks. Hang in there. So I thought these grid patterns were kind of funky and fun to look at. This next group of patterns you don't need to know. These are just for show. But this is another task group 18. This is specific for CT. You can see white, black. You can see little circles inside. If you've got good contrast resolution, you should be able to see little circles inside. So just another kind of a fun pattern. This is task group 18. This is used for making sure that the corners of the screen isn't showing any type of distortion as opposed to in the middle. Task group 18PX is for resolution uniformity. So again, making sure that all of the dots are equidistant from each other, even if you're on the periphery of the monitor. Usually the center is no problem, but as you get to the periphery, you maybe lose some of that detail, and you might lose some of that uniformity. So no problems with that here. Here's one for display noise. So that's kind of it. I did want to talk about a couple other QC things, and this is just for your own information. We have a daily dark test for the Carestream equipment. So if you're not using Carestream, you've probably never seen this before. But if you're at school and you see a daily dark test must be done, it's just a way of kind of calibrating the plate because it's been off, the battery's been out of the back of it. And so this just kind of calibrates the pixels inside. And it also tests the communication with the wireless router attached to the control panel. So that's what the daily dark test is. Again, don't necessarily need to know that. QC for X-ray exposure. Sometimes there is a QC test that requires you to do some exposures to the plate, and that just kind of like warms it up, so to speak. Sometimes you have this to be done on a daily basis, maybe a weekly basis, depends on the manufacturer. This isn't anything that I've seen with Carestream, but I do know that some systems do require that. We used to have a system that you needed to take an image at 40 inches, you needed to take an image at 72 inches, and like I said, it just kind of warmed up the pixels and warmed up the system. So maybe your equipment has that, maybe it doesn't, but it's just nice to know about these QR things. If you're going to be a person who works in the evening, or especially at night, this is usually something that you end up doing, and that's usually why you don't see it being done during the day, because you guys are too busy. And to wrap up this video, other things that the annual inspection is going to cover are things like positive beam limitation, if you've got it, to make sure that when you open up your cones, the cones are the correct size to the plate inside the bucky. It's going to do things to just reassure that X-ray tube alignment and the bucky are always working from the whole span, because you know that table bucky only goes so far to the left or right. You want to make sure that it does use up that whole space. They will also give you that report, and that report is required in order to get your license from the state. The State Department of Public Health is the one that's going to issue that, or the Radiation Control Board for Massachusetts. But generally, the state kind of gives you the list of things that have to be met in order for them to give you your license for the year. So the State Department of Public Health, or for us, it's the Radiation Control Board, which falls under the Department of Public Health. So that's important. Joint Commission, if they're coming around, they'll also want to see these reports to ensure patient safety and proper maintenance of your equipment that you've got. So those are some other things just to consider in real life. And that brings us to the end. This is the end of Module 3. So we're going to be looking at Module 4 coming up next, and then the end of the semester. So a lot of information here. I know this video is a little long, but hopefully you get a better understanding of all of those things that have to be done to have a properly functioning X-ray equipment. So that's it. I'll see you guys later. If you have any questions, let me know.